Good evening, Titans. This is Mr. Simpson, and tonight we're going to be looking at Lesson 6.6, titled Geometric Sequences. And if you recall, when we worked with arithmetic sequences, which is when they had a common difference, we'll now look at geometric sequences that would have a common ratio. So first of all, geometric sequence. In a geometric sequence, the ratio between each pair of consecutive terms is the same. The ratio is called the common ratio, for each term is found by multiplying the previous term by the common ratio. And so we can see here that for 1, 5, 25, and 125, that they're multiplying by 5 each time. Now, a lot of times we find the common ratio by taking, as example, the second term divided by the previous term, which is 5. Then the third term divided by the second term, which would also be 5. And then the fourth term divided by the third term, which would also equal 5. And that's a way we can find the common ratio and determine if they indeed have a common ratio. So first of all, it says, decide whether each sequence is arithmetic, geometric, or neither. Explain your reasoning. So we look at this first one. And again, you may look at it right away and think, okay, what's happening? And go from here to here to here. And again, remember we have to multiply, and it appears that we're dividing by 2, which is the same as multiplying by 1/2. But also, if we take 60 and we divide that by 120, if we take 30 and divide it by its previous term of 60, and we take 15 and divide it by its previous term of 30, we can see that they all have a common ratio of 1/2. So we know that it is a geometric sequence because we are multiplying by a common ratio of 1/2. And letter B, we look at this, we take, and again, if we check for geometric right away, we go 6 divided by 2, well, that's 3. Well, then I take 11 divided by 6, well, I know that's not 3, so I know it's not geometric. So now I'll check to see if it's arithmetic. So arithmetic means that, am I adding the same thing? Well, here I'm adding 4, then I'm adding 5, now I'm adding 6. And again, we're not adding the exact same thing, so it's not arithmetic. Now, there's definitely some type of pattern, but it's neither arithmetic or geometric, so we would say that this is neither. Here we're asked to write the next 3 terms of each geometric sequence. So this is a geometric sequence, so the first thing we have to do is find that common ratio. So we'll just take 6 divided by 3, and that equals 2. And since it says it's a geometric sequence, that's all we really have to do is to find that first constant. So we're multiplying by 2, we're multiplying by 2, we're multiplying by 2. So now if I take 24 times 2, that'd be 48. Now I'm going to take 48 times 2, that'd be 96. Now I'm going to take 96 times 2, and that's going to be 192. And those are the next 3 terms of my sequence. Now here, again, we want to take negative 16 divided by 64, and if we reduce that, it becomes a negative 1/4. So our common ratio is a negative 1/4. So now that's what we have to multiply each term by to find the next 3 terms. So my last term given to me is a negative 1, so I take that times a negative 1/4, and that's going to be a positive 1/4. Now I have to take 1/4 times, again, a negative 1/4, and that's going to be a negative 1 over 16. Now I have to take a negative 1/16 times a negative 1/4, and I'm going to have a positive 1 over 64. So now there's my next 3 terms. Notice how they go from positive to negative to positive because the common ratio was a negative 1/4. Now they want us to graph this. So if we graph this, and again, it's just going to be a quick sketch. So the first term is 32, so I'm going to go up here, and that's 32. Second term is 16, so it's about halfway down from there. Then third term is 8. Fourth term is 4. Second term is 2. And if you look at this, it appears that's an exponential function. So geometric sequences, at least a lot of them, if we graph them, would appear to be exponential. So, equation for a geometric sequence. Well, since we figured out that a graph looks exponential, it makes sense that the equation for a geometric sequence would also be exponential. And so if we look here to find the nth term of a geometric sequence, the a1 is the first term, which is going to be what's multiplied out in front, times r, which is that common ratio, and then raised to the n minus 1 exponent. It'll make a lot of sense why we have to use n minus 1 as our exponent as we go through these. So now here we're going to write an equation for the nth term of a geometric sequence. So again, we're going to take 12 divided by 2, which is 6. So we know that my common ratio is 6 because I'm multiplying everything by 6 to get to the next term. So if we think about our equation, our nth term, a sub n, is equal to the first term, which is 2, times the common ratio, which is 6, raised to the n minus 1. So there's your equation. Now they want us to find the 10th term. So a sub 10 would equal 2 times 6 to the 10 minus 1, which would be 2 times 6 to the 9th. Now remember, you can either plug this into your calculator just the way we have it, or you'd have to do the power first, meaning take 6 to the 9th power first, and then multiply by 2. And if you do that, then the answer you come up with is 20,155,392. Here are a couple more examples you can put in your notes. Again, it's a geometric sequence, so if you look at this, going from here to here, here to here, here to here, it looks like we're multiplying by a negative 5 this time. Multiplying by a negative 5. So my common ratio is a negative 5. And now this is the difference between geometric sequences and actually exponential functions, is that in a geometric sequence, the formula for that, the ratio can be negative. Our a1 is 1, so our a sub n is equal to 1 times negative 5 to the n minus 1. And they want us to find the 7th term, a sub 7. So I have 1 times negative 5 to the 7 minus 1, 1 times negative 5 to the 6th, and then 1 times negative 5 to the 6th is 15,625. And there's our 7th term. This one, it appears that we're multiplying by 2 each time. So again, our common ratio, our r, is 2. Our a sub 1 is 13. So now our a sub n is going to equal 13, because that's the first term, times 2 to the power of n minus 1. And again, if we just look at this example, if n is equal to 1, notice that 1 minus 1 is 0, 2 to the 0 is 0, and or 2 to the 0, is 1, and 1 times 13 would be 13. So the first term is 13, which makes sense why the exponent has to be n minus 1. So now, we want to find the 7th term, a sub n, is equal to 13 times 2 to the 7 minus 1, which would be equal to 13 times 2 to the 6th, which when we do this, we would get answer of 832. All right? So now, that's geometric sequences. That's using them to find the nth term of a geometric sequence and writing the equation for the nth term of a geometric sequence. All right, now I'd like you to open your student journal and have it turn to page 196 and try to complete problems 3, 7, 10, and 14. And we'll check these tomorrow in class. Have a great rest of your evening, Titans, and see you tomorrow.